The overall plan for analyzing recursive algorithms follows the same steps as that used for non-recursive algorithms, with one key difference: how the time complexity of the algorithm is expressed. The process begins by identifying the input size of the problem, followed by identifying or determining the basic operation of the algorithm. If we denote the time complexity by Tn, where n represents the input size, the next step is to establish the scenario for the analysis, whether it is an every case analysis or a best case, worst case, or average case scenario. After that, we move on to formulating the time complexity itself. As discussed earlier, the time complexity of a recursive algorithm takes the form of a recurrence relation in terms of n. Solving this recurrence relation allows us to determine the algorithm's growth rate using asymptotic notations such as big O, big omega, and big theta. To demonstrate how this general framework is applied to recursive algorithms, we will walk you through examples that illustrate each step. These examples will be drawn from real and practical problems. Our first example that we will begin with is an algorithm that computes recursively the factorial of a positive integer. Consider the following formula for the factorial of a positive integer n. N factorial is equal to n times n minus 1 factorial. The formula for the factorial can be expressed as a function with a parameter of n. If f of n gives the factorial of n, then f n minus 1 gives the factorial of n minus 1. So we can replace n factorial by f of n and replace n minus 1 factorial by f of n minus 1. And the formula for factorial of n can be expressed as f of n equals to n multiplies by f of n minus 1. Let's look at the recursive algorithm for computing the factorial of a number n. It works as follows. If n is equal to 1, it returns 1. This is the base case. Otherwise, it returns the product of n and the factorial of n minus 1. That is n times f of n minus 1. For simplicity, we will consider n itself as the measure of the input size, rather than the number of bits in its binary representation. To identify the basic operation, we observe the repeated actions in each recursive call. Testing for the base case, which is a comparison operation, subtracting 1 from n, and multiplying n by the result of the recursive call. Among these, multiplication is the most computationally expensive, so we select it as the basic operation. Since this algorithm behaves the same way for all valid values of n, the analysis does not vary with the specific input. It is not a best, worst, or average case analysis. Therefore, our focus is on determining how many times the multiplication is performed, which we denote by m of n. To express m of n as a recurrence relation, we need to count the number of multiplications in each of its components. I mean the direct solution, which is the base case, the pre-work, recursion, and the post-work components. For the direct solution, there is no multiplication in the base case. Therefore, for n equals to 1, m of n is equal to 0. Before the recursive call, there is a comparison operation for testing the base case and one subtraction for the input parameter. None of them is a multiplication operation. Hence, for the pre-work component, it is equal to 0. For the recursion component, there is one recursive call statement f of n minus 1 with a problem size that is smaller by 1. After returning from the recursive call, there is one multiplication. So for the post-work component, it is equal to 1. As a final result, the number of multiplications m of n is equal to 0 for n equals to 1, and for n greater than 1, it is equal to 0 for the pre-work, plus m of n minus 1 for one recursive call with size n minus 1, and a plus 1 for the post-work. Let's find a solution to this recurrence relation to determine its growth rate and efficiency. To find the solution to the recurrence relation, we will use back substitution method. First, we will write the recurrence relation. M of n is equal to m of n minus 1 plus 1. Now in the draft area, we need to write some of its iterations. The first iteration will be for m of n minus 1. So m of n minus 1 is equal to m of n minus 2 plus 1. The next iteration will be for m of n minus 2, which is equal to m of n minus 3 plus 1, and so on. Let us do the substitution. In step 1, we have the original recurrence relation. In step 2, we substitute for m of n minus 1. So m of n is equal to m of n minus 2 plus 1, because the value of m of n minus 1 is equal to m n minus 2 plus 1 from the previous step. Now in step 3, it is equal to m of n minus 3 plus 1 from the previous steps. If we continue subtracting the value of n by 1, at step k, we can guess the formula as m of n minus k plus k, because we are adding 1 k times. If this is equation 1, then this value of n keeps subtracted by 1 until it reaches the initial value. So here we say until m of n minus k is equal to m of 1, which is the initial value. By equaling the two parameters, n minus k is equal to 1, and from here we have k is equal to n minus 1. We substitute into formula 1, so n1, m of n is equal to m of 1, because the value of m of n minus k is equal to m1, plus the value of k, which is n minus 1. And this is equal to 0 because the value of m1 is equal to 0, plus the value of n minus 1, and this is equal to n minus 1. Now as the efficiency class, this formula, which is linear, belongs to big theta of n. Our next example is a recursive algorithm that determines the number of binary digits or bits in the binary representation of a positive integer n. By looking at the algorithm, in the base case at line 2, if n is equal to 1, the algorithm simply returns 1, since the binary representation of 1 consists of a single digit. Otherwise, in the else block, the algorithm recursively divides n by 2 and adds 1. This is because each division by 2 effectively shifts the binary number 1 bit to the right, and the addition accounts for the digit that was just shifted. Analyze the algorithm and determine its efficiency class. Notice that the question does not specifically ask for a detail or a quick analysis. Also, it does not ask to count how many times a particular operation is executed. It is simply asking to analyze the algorithm. For such questions, you should follow the general framework for analyzing recursive algorithms step by step. I mean, specify the input size and the basic operation, check if the analysis has cases, find the recurrence relation for the number of times the basic operation is executed, solve this recurrence relation, and finally, determine the growth rate and its efficiency class. Let us do that on this algorithm. The first step in the framework for analyzing recursive algorithms is to specify the input size. We could select the number of bits in the binary representation of the input parameter n as the input size. But for simplicity, we will instead use n itself. Therefore, the input size for this algorithm is n. And this will be step number 1. So 1, we have input size, which is n. The next step is determining the basic operation. To identify it, you need to look for the operation that is repeated most frequently and has the highest execution time. In this algorithm, there is one comparison operation in the base case, one shift operation dividing n by 2, and one addition operation adding 1 to the result of the recursive call. Among these, addition has the highest execution time. Therefore, we select it as the basic operation, and this will be step 2. So step 2, the basic operation is the addition operation. Since the addition is executed the same number of times for all values of n, then the analysis is considered as every case analysis, and this is step 3. The analysis type is every case. Next, we determine the time complexity of the algorithm by counting how many times the addition operation is executed. And this will be step 4, the time complexity. Let us denote the number of additions performed by the algorithm by A of n. And this will be the time complexity for the algorithm. The time complexity is a recurrence relation. So we write A of n is equal to. For the direct solution, we do not have additions. So for n equal to 1, we have A of n is equal to 0. For the pre-work operations that occur before the recursive call, we have a comparison operation testing for n equals to 1 and a shift operation dividing n by 2. Since there is no addition, then the pre-work is equal to 0. Since we have one recursive call with input size of n over 2, then the number of additions for this call is simply A of n over 2. Finally, the post-work operations that occur after returning from the recursive call. We have only one addition, so the post-work is equal to 1. And this is for n greater than 1. The last step is solving the recurrence relation and finding its growth rate and efficiency class. So step 5, solving the recurrence relation A of n using back substitution. So first we write the recurrence relation, which is an is equal to an over 2 plus 1. We need to write some of its iterations in the draft area. This is the draft area. First, what is the equation, or what is the value of A of n over 2 equals to? It is A of n over 2 square plus 1. And for A of n over 2 square, it is equal to A of n over 2 raised to power 3 plus 1, and so on. If this is step 1, in step 2, we do the first substitution, which is equal to A of n over 2 square plus 1 from the previous step. In step 3, we do the next substitution, which is A of n over 2 raised to power 3 plus 1 from the previous step. If we continue dividing by 2, at step k, A of n will be equal to A of n over 2 raised to power k plus k because we are adding 1 k times. Dividing by 2 will continue until it reaches the initial value, until an over 2 to the power of k is equal to the initial value when n is equal to 1. So we substitute here and we say equals to 1. Equaling the two parameters, n over 2 raised to power k is equal to 1. So n is equal to the power of k, and from here k is equal to log of 2 of n. If this is equation 1, we substitute for the value of k. So we write n equation 1, the value of a of n is equal to a of 1 plus the value of k, which is log of 2 of n. The value of a of 1 is 0. So this equation will be equal to 0 plus log of 2 of n, which belongs to big theta of log of n. So the efficiency class for this algorithm is logarithm of n. In the following example, the algorithm uses recursion to find the maximum value in an array of size n. It begins by dividing the array into two equal halves by calculating the middle index, which is stored in a variable called mid at line 4. It then recursively finds the maximum value in the first half, ranging from index 0 to mid, and stores it in M1. After that call returns, it recursively processes the second half, ranging from mid plus 1 to the end of the array, and stores its maximum in M2. After returning from this second recursive call, it compares M1 and M2 and returns the larger of the two. In this example, it is required to analyze the algorithm and determine its efficiency class. To analyze the algorithm based on the general framework for analyzing recursive algorithms, we start by specifying the input size. Step 1 is the input size. The input to the algorithm is an array of size n, so n will be the size for the algorithm. In step 2, it is to identify the basic operation. So here we need to specify the basic operation. In the given algorithm, the base case includes one comparison operation, checking if n is equal to 1. In the recursive case, the algorithm performs a shift operation, dividing n by 2, an addition operation adding 1 to mid, and another comparison operation comparing M1 with M2. Although addition typically takes slightly longer to execute than comparison, both operations occur a constant number of times. Therefore, either could technically serve as the basic operation. However, it is more appropriate to select comparison as the basic operation because the algorithm fundamentally relies on comparing elements to determine the maximum value in the array. The addition is secondary and only helps divide the array. Thus, we define the basic operation as comparison. Step 3 is determining the analysis type. Analysis type. Since the number of comparisons depends only on n and does not depend on specific values of the array, then the analysis is every case. And step 4 is finding the time complexity. And to find the time complexity, we say let Cn be the number of comparisons. Then C of n is expressed as a recurrence relation. So C of n is equal to For the base case, there is only one comparison, and this happens when n is equal to 1. So for n equals to 1, we have one comparison. Now for n greater than 1, there is no comparison in the pre-work component. Since the algorithm has two recursive calls, each supplying half the size of the array, then the number of comparison for both calls is Cn over 2 for the first call plus Cn over 2 for the second call. Finally, for the post-work, we have one comparison, so we have a plus 1. Rewriting the recurrence relation, Cn is equal to 2 Cn over 2 plus 1. The last step is solving Cn using back substitution method and determining the efficiency class. And this will be step 5. So step 5, solving Cn using back substitution. We write the recurrence relation Cn is equal to 2 Cn over 2 plus 1. In the draft area, we will write some of the iterations for the recurrence relation. First is Cn over 2, which is equal to 2 Cn over 2 square plus 1. For Cn over 2 square, it is equal to Cn over 2 raised to power 3 plus 1, and so on. So let us start the substitution. If this is step 1, in the first substitution, 2, we substitute for Cn over 2 by 2 Cn over 2 square plus 1 plus 1. Simplifying the equation, we have 2 square times Cn over 2 square plus 2 plus 1. And this is for step 2. Now the next substitution is for the value of Cn over 2 square. So we have 2 square times 2 Cn over 2 raised to power 3 plus 1 plus 2 plus 1 from the previous step. Simplifying this equation, it is equal to raised to power 3 Cn over 2 raised to power 3 plus 2 square plus 2 plus 1, and this will be step 3. Continuing the substitution, at step k, the equation is equal to 2 raised to power k Cn over 2 raised to power 3 plus. We will have a summation, and if we take the summation from right to left, we have 2 raised to power j. Notice this one is 2 raised to power 0. And this j starts from 0, it goes up to k minus 1. Why? Because see, at step 3, the last power is 2. Step 2, the last power is 1. So the last power at step k is k minus 1. And this is equal to 2 raised to power k Cn over 2. I think I made a mistake here. I should write k, 2 to the power k, plus the closed form formula for this summation, which is a geometric summation. It is 2 raised to power k minus 1. We label this formula by 1. Then continuing dividing by 2 until C n over 2 raised to power k equals the initial value, which is C1. So if we go back to the recurrence relation, this is the initial value when n is equal to 1, then C1 is equal to 1. By equaling the two parameters, n over 2 raised to power k is equal to 1. So n is equal to the power of k. So k is equal to log of 2 of n. Now substitute into equation 1. Cn is equal to, now for 2 to the power of k, it is equal to n. So here we will have n C1 plus, again for 2 to the power of k, it is equal to n. So we have n minus 1. And this will be equal to, since C1 is equal to 1, so we have n plus n minus 1. We have 2n minus 1. And this belongs to big theta of n. So the efficiency class is linear.